In this video, I want to talk about some of the basic definitions of rings and how certain sources disagree about how you should define some of these key concepts. So let me start by just recalling the definitions that we've talked about from Dummit and Foote so far. So a subring of a ring R is an additive subgroup of R that is closed under multiplication. Remember, rings don't necessarily have to have an identity. And let's suppose that you're in the case where your ring R does have an identity, 1, that's not equal to the additive identity, 0. Then an element U in R is a unit if there exists a V in R such that U times V equals V times U equals 1. And we've seen that the set of units R cross is a group under multiplication. So we already mentioned this weird example where we have Z mod 6Z as a ring. It has an identity, 1, and the group of units is 2 elements, 1 and 5. These are the 2 things that have multiplicative inverses in this ring. This subset 0, 3 of Z mod 6Z is a subring. It's closed under multiplication, and it's a subgroup under addition. And it also has an identity for any non-zero, or yeah, I mean, it has an identity 3. 3 times 3 is 3. 3 times 0 is 0. So it satisfies the things that it needs to be the identity of this ring of 2 elements. And the units in this set are just the single non-zero element 3. So I want to talk about some issues raised in these notes by Conrad called standard definitions for rings. This is a short document, and I'll talk about this in this video and also in the next one. So in Conrad's definitions, a ring has to have an identity, 1. And a subring of a ring R is a subset R prime that is a ring under the same plus and times. So it's an additive subgroup using the same plus, and it's closed under multiplication, just like up here. But the big difference is, okay, a subring has to be a ring, so it also has to have the multiplicative identity, has a multiplicative identity, and we're going to insist that the multiplicative identity of R prime is the same as the multiplicative identity of R. So let's look at this example. 0, 3 inside Z mod 6Z. This is a ring under the same plus and times, but it has a different multiplicative identity. So with this definition, this subset is not a subring. Okay, so I'm going to pause and erase, and then I'll talk about why you might want to have this definition for subring, and in particular, consequences, like very natural things that you can prove about how the units of R prime are related to the units of R. Let me start by saying something about how big an assumption this is, that your subset R prime in R that is a ring under the same operations plus and times has to have the same multiplicative identity. Remark 2.4 in these notes of Conrad says that if R has cancellation for multiplication, this isn't an extra assumption at all. So more precisely, R has cancellation for multiplication. What that means is if xz equals yz implies x equals y, if you can do something like multiply both sides of this equation by z inverse, if that's a thing that makes sense, which we've seen it is, for example, in the case where R is an integral domain, we proved that if you're an integral domain, you do have this cancellation property. Then if you have a proper subset, R prime of R, that is a ring under these same operations, plus and times, then it must have the same multiplicative identity and be a subring. So you can't end up in this weird case where you have a ring that is a subset, but the multiplicative identities are different. So let's see why that's true. So let's say that x in R prime is the multiplicative identity of R prime. Then in particular, x times x is the same as x times 1, where 1 is the multiplicative identity of R. So why is that true? Well, x is in R prime, x is also in R. X times x, this is equal to x, which is the same as x times 1. So now we have an equation in the ring R that has cancellation for multiplication. So x times x equals x times 1. That means either x equals 1 or x equals 0, and this equation is just 0 equals 0. So what I should say is xz equals yz implies x equals y, or z equals 0 is this other case I want to put in here. Okay, so what have we seen? If you have this cancellation property, then if you have a subring that has a multiplicative identity, it must be the same multiplicative identity. So what goes wrong when we look at this example here of the subset 0, 3 inside Z mod 60? Well, this is a subring. I mean, it is a subset that is a ring under the same plus and times, but the multiplicative identity here is 3. So when we get to this point in the argument, 3 times 3 is equal to 3 times 1. That's true, but it's just not true that 3 is equal to 1. Why? Because this ring Z mod 6Z does not have this cancellation property. So we can't conclude the argument in the same way. I mean, 3 times 3 equals 3. If you remember how the cancellation property proof worked in an integral domain, you subtract and you get 3 times 3 minus 3 equals 3 times 3 minus 1 using the distributive property. And these two things are multiplying to 0, but neither one of them is 0. So in Z mod 6Z, that's just life. There are a bunch of 0 divisors, and 3 and 2 are 2 of them. But in a ring that has this cancellation for multiplication, this isn't adding any extra assumptions. Okay, so now I'll pause and erase, and I'll talk about a consequence of this definition for units in subrings. Let's state and prove a fact about units in subrings. This is theorem 2.5 in Conrad's notes, and it's really important now that we use Conrad's definition of subring, where rings have a 1. Subrings not only also have to have a multiplicative identity, but it has to be the same multiplicative identity. Okay, so if R is a ring and R prime is a subset of R that is a subring, then the group of units in R prime is a subgroup of the group of units in R. And why is it so important to use these definitions? Well, in Dummit and Foote, the subset 0, 3 is a subring of Z mod 6Z. This is a subgroup that is closed under multiplication, and this statement is just not true in this example. The units here are just 3. The units here are 1 and 5. So Dummit and Foote acknowledge this. This actually comes up. This is an exercise in section, I think this is an exercise somewhere. Okay. Let's prove this. Let's say that 1 is the multiplicative identity of R. That means that because R prime is a subring, it is also the multiplicative identity of R prime. So where does this proof go wrong in this example? In the very first sentence. I mean, this statement just isn't true if you don't require R prime and R to have the same multiplicative identity. So let's take an element of the units of R prime. And we know that R prime has the same multiplicative identity as R. So what does it mean for X to be a unit? It means there's some Y in R prime, so that X times Y equals Y times X equals 1, the multiplicative identity in R prime. But we know that this is also the multiplicative identity in R. X and Y are also elements of R. So Y satisfies the things you need to satisfy to be the inverse of X in R. So X is also a unit in R. So what are we seeing? We're seeing that the set of units in R prime is a subset of the set of units in R. So we want to say more than it's just a subset, that it's actually a subgroup. So we need to say that the group operation in R prime units is compatible with the group operation in R units. But multiplication and inversion in R prime are the same as they are in R. Like if you have two elements, A and B, in R prime and you multiply them, that's the same thing as multiplying those two elements in R. Same thing for taking an inverse. The inverse of A in R prime is the same inverse that you get from taking the inverse of A in R. So that means that the group operations are compatible and R prime units is a subgroup of R units.